Check it out now, y'all.
nanoHUB-U, online instruction.
Well, this is the end of week 2. I had a lot of fun talking about the equilibrium properties of battery materials, how the chemical potentials specify the voltage and the solubility limits of the different phases. It was, if you think about it, it was a deeply theoretical week. The concepts that we developed apply not only for the lithium system, but they apply for the generality of electrochemical systems. So today I want to talk about something that I think is very exciting, where concepts like the one we discussed apply directly, but they're a little bit more industrial than what we have been discussing during lecture. In this case, I want to focus on the sodium nickel chloride system. Just to put it in perspective, this presentation, this work that I'm going to tell you about today is actually something that GE presented in the 2009 TMS meeting. The people that should actually get the credit for this work are Rahmani, Yakovangelo, Valens, Sarafinor. All of them, they have been developing this technology that, from what I read recently, has been actually commercialized, and people are actually making these batteries. So, what is the motivation for the work that they perform? These types of batteries, the sodium nickel chloride system, are actually used these days on trains, on engines for trains. Typically, a train has it runs on diesel. A classic train runs on diesel these days, where you have between 2 and 3 engines that you have as backup in case one of them fails, so that you can get the power that you need. My understanding is that not all of them uses all the energy that is required to move the train. But if you ever watch a train as it approaches a station, you will see how it takes a long time for that train to slow down and come to a stop as it arrives to the station. And mostly because the train has to work against the accumulated inertia that it has, the large mass that the train has, and it really has to slow down for quite a while until it finally meets the station on the right mark. So all that energy, all that momentum, it would be great if we could somehow capture it and use it to also power the same train. So that's the concept that they developed. And in this case, you can see the energy is such that we take the energy from the diesel to move the engine, and when we brake, we of course pass 10% of that energy to some battery, to some means to store that energy, so that by doing that, we get a 10% fuel saving. That's a lot of savings, and you think about it, and a boost of the horsepower that the system has. And what I found also more interesting, as compared to lithium-ion batteries, where we have been having a 2-year turnout, basically every 2 years we have to be thinking on replacing the batteries. In this case, they have a 20-year life, which I think it's great. So the thought is to take one of these diesel engines and remove it and replace it instead with a rechargeable battery that uses the energy of the inertia of the train itself to power itself. Okay, and now what type of battery would you require, without forgetting for a second that the answer is the sodium nickel chloride system? Okay, really what we have is we need to distinguish between high energy and high power. In general, we cannot do both. Okay, you can think of on one side having, or at least graphically, high energy. You can think of a large jug of milk where you accumulate a lot of energy in a large volume. Okay, and on the other side, where you have a lot of power, basically you can accumulate a small amount of energy, but you can take it out and put it back in really fast. That's what gives you the high power in the system. And in this case, the Ragone plots, as we have discussed them in the last 2 weeks, you have here power versus energy. Mostly the systems that we're aiming for are somewhere over here. Notice where lithium ion sits, right, where you have on the order of 100 watt-hours per kilogram of energy. While the sodium nickel chloride system basically compares these days with lithium ion batteries, and the projection is such that the energy density will increase as they improve on this technology. And well, it seems that they can double it in the near term to improve the performance. So, and well, in this case, batteries as they currently are being used, you can see that, well, in this case, sodium will be a high energy density system. Lead acid will be something in between, and supercapacitors gives a lot of power because all the energy in this case is stored in internal surfaces, and that's why that one is over there in this plot. So this is just from the material perspective as you're trying to pick your right chemistry to improve on your performance. Now, when it comes to actual application, I mean to the vehicle that you're going to move, well, you care not only about the power, as we saw in the previous slide, but you also care about the energy. And in this case, you would like to have power and energy at the same time. Okay, so you can see how on one side we have economy vehicles where you have you would expect here to have a high energy turnover. And on this side, the hybrid locomotives, you would require not only high energy but high power. So you have the whole range in between of how, in one side you can basically deliver the energy and power density that you need, as compared to being limited or constrained by having high energy or high power. Okay, so what is interesting about this slide is that as you plot the peak power and peak energy on one side, you can get a large amount of wattage, but low energy amount of energy stored in it, giving you a power versus energy ratio very large. But as you go and increase the energy, that ratio basically becomes much smaller. So really, where you would like to be really somewhere here in between, where you get both of them, okay? And ideally, you would like to basically, increase both of them. Now, the advantage, in this case of the sodium nickel dichloride system, is that you actually get a large amount of energy. That's main, well, I wouldn't call it a shortcoming. Its main characteristic is that it runs hot. In this case, that type of battery runs on the order of 100 and 200 degrees centigrade. And well, this is just a sketch of that system. And what you have here is in this gray zone corresponds to the nickel dichloride system mixed with an electrolyte of sodium aluminum tetrachloride system, right? That's its mix here on the background. And here you have this molten sodium. Basically, you need to bring your battery all the way up to the molten state to start running, which actually, if you think about it, in a locomotive is not too difficult to do, because once you have reached that temperature, even though you have to invest some energy in actually heating up your battery, the reaction as it performs is exothermic, so the reaction is self-sustained. And well, the idea is that you have, separating both of them, you have this alumina separator through which the sodium ions are going to move through. Now, this structure, this is just a sketch. The sodium nickel dichloride battery was actually invented at the end of World War II in South Africa, and they're referred to as zebra batteries. If you bring that technology to the modern age, it's really not used in that simple system, but basically what you do is you take that alumina separator, that alumina boundary that separates both phases, and actually maximize the area by basically crumpling it, okay? And in between here, what you have in the middle is you put the cathode material in powder form, okay? And in the background, you basically, that's where you put your sodium that basically is liquefied. And here what we're seeing here is a cross-section of that structure that really corresponds to a top view of this canister. And what you can see here, this square in the middle is basically a cross-section of the current collector. In this case, a carbon wick that you use to maximize the area so that you can collect as many electrons as you can. And this two circles is basically a cross-section of this nickel current collector that you're using to hold that carbon wick in the system. Now, this is just one cross-section. fundamentally the reaction is made in this way. This is now a side cross section where this is the wick that we were talking about. You can see inside the nickel sodium chloride and plus additives, including the electrolyte in here. Okay, the alumina jacket that separates the liquid from basically the anode from the cathode. Okay, and of course the case, which is some steel. Okay, and the reaction proceeds in such a way that you start by having your liquid sodium. Okay, that basically you dissociate into sodium ions and electrons, just like in the batteries that we have been discussing. The electrons are removed by the back contact. They enter here they go through the resistive load, and then they just enter on the other side, while the sodium ions are going through the separator region, through the alumina solid, that at that temperature actually they're quite mobile. They cross to the other side, and then those sodium ions react with the nickel dichloride and the electron as it went through the resistor to form, in this case, salt, table salt, plus nickel in the other side. That's during the discharge. During the recharge, well, basically we are using the braking of the locomotive. We force now electrons from the cathode back into the anode. Basically, we dissociated that sodium into 2 electrons. And we basically force the sodium ions across through that electrochemical potential that develops, putting more sodium in this side. So as the battery discharges and we're moving sodiums from one electrode, from the anode to the cathode, basically the amount of sodium in liquid form basically comes down, right, as it diffuses on that side. And when we recharge it, we basically bring it back up. Okay, these are several of the components as they're being used. You can see this is a more three-dimensional view of the same system. Well, clearly they basically cut here so you can see it, but you can see that not only it's here separated through the alumina contact, but also they put an alumina collar to further insulate the system. Okay, and the entire capping system and the rings are set up in such a way so that to prevent, in this case, to accumulate gases in the system. And what you can see here, this is showing you the different components as we have them. You can see this as the granules of the cathode as we just described it in the previous slide. And what I find interesting is that notice what fraction of the battery, actually the entire battery in a per weight distribution actually corresponds to active material, as compared to a lithium-ion battery, which basically is around 40%. 40% that constitutes the actual cell. In this case, it's a little bit more than 50% of the cell that is actually electrochemically active. Notice that there's a big section of alumina because of its density. It's being used, but they made a very good job at minimizing the seal components, the casing, and all the other stuff, as you can see here in the section. Oh, and you can see here in this white X corresponds to the alumina casing. Okay, and this is just another view, right, showing you how they have the electrolyte in solid form and the nickel plus sodium chloride, and you can see in this case, very straightforward to get that chemistry. My thought is that they're not exactly necessarily using this chemistry. You can think of a great opportunity on science to basically improve on that chemistry as well, right? Not necessarily, basically maybe dope it with something to improve on its performance. Although, of course, I don't know the details of exactly what they're doing, right? That said, this is not the type of battery you would have, in the back of your or in your garage, because of such a high temperature. It really requires a specialized location, a specialized lab to do it, and clearly GE has the infrastructure to do that. It seems to be quite straightforward, at least quite simple, as to how this technology, it all focuses on the overall sauce to describe it. Now, this is from the point of view what that technology is currently doing and what are the different components. Okay, from the point of view what we learned this week, we really have a system that not only where you not only have the transfer of one ionic species, but you now have three components in this system. You have the sodium, the nickel, and the chlorine in the system. So that makes our equilibrium to differ from a simple two-component phase diagram, but now we have to look at a three-component system. Okay, and in this case, we look at it by specifying, in this case, an isothermal ternary phase diagram where one corner corresponds to the sodium rich, another corner for the nickel rich, and the other corner where you have only chlorine. Okay, the overall reaction, as you can see here, is you have two sodiums that react with nickel dichloride, lead to the formation of table salt plus nickel. Okay, and we would like to first, of course, identify each of these components, okay, because at equilibrium they will define the free energy of the system, and they will define of course, as we discussed this week, the potential of the cell. In this case, the free energy of the reaction, the free energy of transformation for the right sodium, nickel, and chlorine composition defines that Gibbs free energy of transformation or the potential of the cell. Okay, so what we would like first to identify, for example, the sodium chloride. Notice that in this case we're saying that for each sodium we have one chlorine, so it should be right in the middle between the chlorine corner and the sodium corner, so it should be somewhere right in the middle. I'm going to highlight it there. Okay, and this part over here is basically what one of the products of the reaction is, or one of the reactants, right? Depending if we're going forward or backwards in this reaction. Another important component besides the sodium, which will be this corner, and the nickel, which will be this corner, is the nickel dichloride. In this case, we're saying that we are 2 times closer to chlorine as we are to nickel. So if we divided this line in 3 parts, it should be somewhere here because we're much closer to chlorine than to nickel. Okay, and that corresponds to this corner over here. Those are now we have all the reactants associated, associated to this reaction. Okay, I think that an interesting contribution here is the sodium chloride and nickel reaction. Basically, there's a whole set of mixtures where sodium chloride and nickel can coexist in this fraction that corresponds basically points along this line, which I can also highlight. Okay, and that corresponds to this line. Basically, anything that where we have that composition correspond to this one line. Similarly, the sodium chloride and well, actually you have it here. The sodium chloride and the nickel dichloride in principle should be at equilibrium too. Okay, so for that case, that corresponds to this line over here. So now that we have identified these 3 lines, these locations and these 2 lines, then really what we have here is we have the final region where this battery will actually perform, which would be anywhere within this triangle. Why? Because outside these lines, basically, we're away from that composition, and we're either too chlorine rich or sodium rich. So if you put too much sodium, we will be away from this triangle, and therefore the battery will not perform. And we basically are constrained to this triangle. Now, since we want to basically specify the amount of sodium through which this battery will perform, we're talking about going from this corner to that corner, which corresponds really to that dashed line. Effectively, the reaction starts right at this point and proceeds all the way until you end up with you run out of nickel dichloride. So it really is within this distance. And if you do that, well, that means that the system is at equilibrium in that one corner. Okay, that allows us to specify the reaction of the system. And you can see here how if I divert from this one spot, I can have the same potential that the material expects, but you will have this additional extra material that may impact on how this reaction performs. So overall, that corresponds to this free energy of transformation. Okay, and if you divide it by ZF, that will give you, in this case, a potential of 2.59 volts, which basically allows you, in this case for this cell, to provide a current of 45 amps. And if you think about it, that's a very nice cell. This voltage is very competitive with current lithium-ion batteries, giving that current. The only shortcoming is that, again, you have to run it hot. You have to run it, say, roughly around 300 degrees C in order to have this reaction to be favorable. And as a result of that, well, this is not something you would put on your everyday laptop, but it's something that you have to run separately like they do it in an engine. And I think it's a very neat example on how we can bring thermodynamic concepts to explain the voltage of the cell, and how understanding where we are in this phase diagram, we can effectively specify the range of composition and performance of the cell. Thank you.